All right, let's dive into a question that sounds super simple, but actually unlocks the secrets to, well, everything around us. What is stuff really made of? Today, we're going to explore the particulate nature of matter. Okay, picture this. You're walking along a riverbank. You've got these huge rocks, right? And then smaller pebbles, and of course, super fine sand. We've all seen how, over time, the river just smashes those big rocks into smaller and smaller pieces.
So that gets you thinking, doesn't it? Does this process just go on forever? If you could take one of those tiny grains of sand and just keep breaking it down, would you eventually hit a wall? A point where you just can't break it down any smaller? Is there like a fundamental, smallest possible piece of rock?
So, yeah, how small can we go? To figure that out, we're going to have to do a little detective work.
And we can start with something really simple, something you can probably picture in your head right now. A piece of chalk. All right, so you grab your stick of chalk. Simple. Then you snap it in half, you keep breaking those pieces down and down until they're just too tiny to break with your fingers. And for the final step, you grind them up into a really fine white powder.
Okay, now lean in and look really close. Even as this super fine powder, every single one of those tiny little grains is still chalk. All we've done is change its size. It's a physical change, not a chemical one. The chalkness, if you will, is totally still there. Okay, so that brings us to the next big question. The powder is made of tiny grains we can see, but what if we could keep going? What happens when the pieces get so small that they're just invisible? And to figure that out, let's turn to a little magic trick that you've probably done in your own kitchen. We're going to take a spoonful of sugar and stir it into a glass of water. So you stir, and poof, the solid sugar crystals just disappear. They're gone. But wait, take a sip. The water is sweet. The proof that the sugar is still in there is in the taste, even though you can't see it for the life of you. So where in the world did it go?
And that is the secret behind the trick. The sugar didn't just vanish into thin air. Nope, it broke down into millions and millions of individual particles, each one so ridiculously small that it became totally invisible. They just spread out and hid in the little gaps between the water particles themselves.
So, this whole idea of invisible particles, that's the key to everything. It opens up this entire microscopic world that has its own set of rules. So let's dive into the world of particles. Okay, first up, let's get some vocab down. These basic, tiny little units are called constituent particles. It doesn't matter if we're talking about chalk, or a rock, or sugar, everything is made of these fundamental building blocks. Right, so let's go back to our sugar water. How did those sugar particles even fit in there? Well, it turns out that water, at a microscopic level, isn't just a solid block of water stuff. There are actually tiny empty spaces between all the water particles. And those little sugar particles, they just slipped right into those gaps. We call these interparticle spaces. So you might be wondering, what keeps all these particles from just, flying off in every direction? Well, there are these forces of attraction between them, kind of like a microscopic glue holding them all together. We call these interparticle attractions, and you're going to see just how important their strength is in a minute. And you know what's really cool? This is not some new idea. We're talking thousands of years ago, when the Indian philosopher Acharya Kanad was already talking about how all matter was made of tiny, indivisible particles that he called parmanu. Pretty amazing, right? The hunt for the building blocks of our world has been going on for ages. Okay, now for the payoff. We're going to put everything we just learned together. Using this new model, particles, spaces, attractions, we can finally explain something we see every single day: solids, liquids, and gases. Let's kick things off with solids, like a chunk of iron. In a solid, the particles are just packed together super, super tightly. The forces between them, those interparticle forces, are incredibly strong. They lock every particle into a fixed spot. They literally can't move around. All they can do is just vibrate in place. And that is why solids have a fixed shape and a fixed volume. And just to show you how different those forces can be, think about this. To melt ice, you only need to get to 0 degrees Celsius to break those particle attractions apart. But for iron, man, the forces are so powerful, you have to crank the heat up to over 1,500 degrees. That's a huge difference. Okay, so what about liquids? Well, in a liquid, those interparticle forces are weaker. They're still strong enough to keep the particles hanging out together, which is why liquids have a fixed volume, but they're not strong enough to lock them in place. The particles can just kind of slide and tumble past each other. And that's exactly why a liquid can flow and take the shape of whatever container you pour it into.
And last but not least, we've got gases. In a gas, it's a totally different story. The particles are super far apart, and they're moving incredibly fast. The forces of attraction between them, practically zero. We say they're negligible. This means they just fly around like crazy, bouncing off each other and the walls of their container. And that is why a gas has no fixed shape and no fixed volume. It'll just expand to fill up any space you give it. So really, it all boils down to this, doesn't it? The things we can actually see and measure, like shape and volume, are a direct result of that invisible dance happening between the particles. How strong are the forces holding them together? That one question determines everything. It all just connects.
Wow, so we've gone from a simple rock on a riverbank all the way down to the invisible particles that perfectly explain solids, liquids, and gases. But it makes you wonder, right? What happens if you take a gas and just keep pumping it full of more and more energy? What happens then? Well, that's a question for another time, and it leads to a whole other pretty wild state of matter. Thanks so much for joining me.